Okay.
Hello, everyone. I want to welcome you to the ACIL webinar series that we have for the year 2017. You can see what I'm showing on the first slide down at the bottom. We did one on February 15th on the Technical Management Committee of U.S. National Committee of the International Electrotechnical Commission. This one I'm going to bring the listeners and viewers up to date on what's happening in the SmartGrid area, and in particular what's happening in the Electromagnetic Interoperability Issues Working Group, which I chair, and that has direct application to electromagnetic compatibility testing. Then in May, we're going to review what comes out of the C63, Accredited Standards Committee C63 on EMC. They meet earlier that month. And then in June, we will have gone through another IEC Advisory Committee on EMC meeting. Actually, it's in the first week of May, 2 weeks from now. And then we're going to take a break because a lot of these committees do take breaks on the summer solstice, so to speak. And then I'm going to come back and give a review of what was happening at the CISPR meeting in Vladivostok, Russia. I will have to rely on the handouts that I get and the agenda because I will not be attending, but I will have access to most, if not all, the material. Then we'll close the year on the 28th of November. That's a week after Thanksgiving with the last ASEC meeting as shown in the 28th of November. So we have 6 webinars. One is under our belt. These are all recorded, and they are available for free of charge to ACIL members on the ACIL website. If you want to have the instructions on how to get to the right place, it's a couple of clicks, and Bob Utenweiler will give you some suggestions on how to get there, or you can send an email to me and I'll try to send out those instructions. So we will, all these webinars are 1 hour in length. I try not to go over that. In fact, I do not go over that. And if I have to miss a few things, we can catch it on the next webinar later in the year. So with all that said, let's get started. And let me see why I can't get started. Okay. Interesting, it gets into a mode that won't allow me to advance, but now I found out. All right, the title of this webinar, as you can read, I'm going to do some selected standards that's used by the SmartGrid Interoperability Panel. That's what SGIP stands for, and it has a new name, which I don't think is of importance for this. It's SEPA, which brings in renewable energy as well as power over the grid, and therefore they're into solar and windmills and things of that nature. So it's a much larger organization, and there's roughly 5 times the number of members that are in the SGIP. ACIL is a voting member of the SGIP, and if you look at the Interoperability Issues Working Group, I chair that on behalf of ACIL. And if you look down at the bottom there, you'll see that I'm also vice chair of the SmartGrid Testing and Certification Committee, which is one of the standing committees of SEPTA SEPA now, but it was SGIP. So we get a lot of visibility for ACIL, and the whole point is to take that visibility in the other direction to give it to ACIL members or those that want to view the recorded version of this and pay a small fee. Okay, let me just kind of go into the EMII working group. I'm going to bring up a link here, and hopefully everything works. I think it does. If you go to the SGIP website, and again, this will be changed to SEPA at the top left. This is the home page of committees. And if you look at domain expert working groups, they call them DUGs. These are special topics that have working groups to work on that. And you can see that the second row over, I'm not sure why they always use light blue font, but they do. If I bring up that link, it is a overview of what the working group does and its goals and the abstract. The description is we access the impact of the EMI environments because that's really the issue. There's little emission problems at the moment, but it's more immunity. Our goal is to identify the environment from the customer location through the distribution up to the generation plant of the power. And there's a list of, the abstract of what we do, etc. We have several white papers that have been published. The ones that I put on this home page are two. If you click on those, you can bring up those documents. I don't propose to do that right now. But we did one on testing of communication networking, which is probably a more unusual thing that is not necessarily done in box testing for immunity that EMC people do. There you look for performance degradation criteria, acceptance criteria, and it's generally that the device continues to work after the application of a transient of some sort. When you go into the SmartGrid, you also, because the smart part of it is the communication channel, which you communicate in both directions, from the customer to the utility, utility to the customer, so they can have an efficient trade-off of when they need power, and therefore they have the ability to say, we'll use the power in the low cost part of the evening or early morning. And if there's any issues of things not working, then of course you have a two-way directional communication. So in addition to, it's kind of like the mode of operation when you test the equipment under test. Here, that mode of operation is a continuous communication channel, and therefore you can imagine that the testing for that is rather specialized. For example, things like bit error rate comes into play, which normally we don't worry about in information technology equipment testing, unless the manufacturer says that this is a critical thing that has to be monitored in an immunity test. So I thought you ought to see with that link where you can find more information. Now it's, I always put this picture up. If you look at the top from left to right, this is typically what we do right now in the power grid. We have a generation, and it either can go over to an industry area or it can go over the far right to a residential area. And it's in the middle, it's usually a high tension transmission line at hundreds of kilovolts, and then it's stepped down with transformers as you move on to 120 or 220 volts or 240 volts at your split power that you get at your residence. The bottom row, however, is now the overlaying of a communication grid. And remember I said we have to communicate backwards and forwards. If you look in the middle of there, you can see that most of the things that are being done in the United States, and Canada for that matter, is done with wireless communication. Now, clearly there's communication over the power grid to switching in capacitor banks and load factor correction. But the smart grid part of it generally is a wireless communication and control. If I put this, if I put a picture up with the European community, their power grid is buried below ground in general. Well, wireless isn't going to work too well. So what they rely on is power line communication under 150 kilohertz, and they put a signal on the power line, and the power line then represents the transmission line. And of course, the question we have always is that going to somehow leak out and interfere with radio services or other? And obviously, one of the things that we always try to do is look at the balance of the transmission line, because it's the balance of the signal put on it and the conversion to longitudinal in common mode on both conductors that is an antenna, both in radiating and of course in the opposite direction is the receive antenna. And the way we do it is to know the balance of whatever transmission line. Well, guess what? What do you think the balance is of the power line? I can tell you right now, you can pick a number, pick any number. We don't know. We don't know. So the question is, how do you make sure that power line communication doesn't end up radiating off of the unbalanced power line? But that's a much longer discussion, and we don't have time to go further than what I'm just saying right now. So think of SmartGrid as the regular infrastructure plus the intelligence overlay. Now, getting into the SGIP, they have member groups, and the top left is just the title is working groups. The middle is priority action plans, and you can see by some of the titles they have specific tasks that they're trying to perform. For example, they're working on one on energy storage. And then on the far right is what I call more administrative side, and that's the standing committees. They have one on the grid architecture. Of course, cybersecurity is a major concern. Testing and certification, well, I'll talk a little bit more about that later on, but that's where the EMII working group has a close relationship, and as a consequence, I made sure I was on the leadership team of both. And then, of course, going now back to the far left column, you can scroll down to, I have shown it completely, to the EMII working group. And that's what we're going to focus this particular webinar on. And as you can see, it's duly noted as one of the major working groups in the SGIP. So a little bit about our charter. The red part is just sort of the highlighting it that I'm talking to in the webinar here. We want to enhance the immunity of smart grid devices and make sure that it works where it's located. And that means it has to be immune to sufficient immunity to both radiated and conducted interference. So given that that is sort of the overarching need, we then work on recommendations on applying standards and testing criteria so that this can actually be tested in the laboratory, or in some cases there are test beds out there where they actually have put together aerial cable and in particular put a SmartGrid I guess communication channel on it and test it for real as if it was a real installation. Well, for our purposes, we're going to look at this as a laboratory test vehicle. So the issues we have is, how do you avoid these issues? How do you avoid the RF environment? And as you might imagine, that's not simple, especially since if you look at where are the overhead power lines? In fact, the question should be, where aren't there overhead power lines? So we will then address these topics one at a time, and the idea is we will bring in a material from the International Electrotechnical Commission as well as the IEEE and others like that are appropriate. So our approach is to actually work with the utilities, manufacturers of these, let's just pick out a smart electronic device as opposed to a smart meter, because we have much more than just meters on a smart grid enabled grid. So we start calling them smart electronic devices. And obviously we have experts on our working groups that are very knowledgeable, and I'm going to go into one specialty later on in the webinar on high power transients. So, and other SDOs like the IEEE and the IEC, of course. So we actually have sent out surveys to the power industry and the manufacturers of actual devices. And as you might imagine, from an EMC perspective, some of the power folks didn't know what we were talking about. Others said, well, we rely on the manufacturer if it's a utility that's talking. And when we sort of drove down, peeled that onion, we found that the manufacturer may not have done any testing whatsoever. And then on the other side, there are some manufacturers that do a respectable job in testing, against lightning and surge and things of that nature. So once we have that information, we try to evaluate and initially do development of standards. A lot we're doing right now is more on the criteria for what is operable and what's not operable, rather than sitting down and writing a standard. But we have documents of manuals and application guides that we're working on. We have sort of a mantra, you can't interoperate unless you can operate, which means if the device itself is destroyed in some sense because of the environment, you're certainly not going to interoperate because you can't get a signal through that device. So we, in fact, at one point we were thinking about getting a t-shirt made with that, but that was a little bit over the top. So let's go into most recent activity, and I mentioned one already on manuals. This interoperability process reference value, the IPRM. You'll hear IPRM anytime you go to an SGIP meeting, and probably says, well, what is that? Well, if you look at the bottom, there is now a ANSI NEMA standard, SG-IPRM-1, that was published late last year. And now go back to the top. What I was able to do is to get them to insert a section on EMC, which was not there before. They had cybersecurity as one of the aspects, and of course the interoperability itself, the communication channels and that aspect, which is obvious. But there was an EMC void, and that didn't sit well with us. So here is the, I just took part of a chapter of the IPRM, in fact, clause 7.2, as you can see. And there it says, as in the case of cybersecurity. The reason why I did that is 7.1 is cybersecurity, and it had been well documented. And I felt that it was useful to end up using the same format that we did for, that was there for the cybersecurity, so it didn't look, quote, out of place. And because of that, we have, they have their cybersecurity, and we based our work and what we talk about. In fact, these are exact words from the document. So we based on incident of EMC problems already experienced by utilities, uncover design, implementation of these operability tests, etc., as not having sufficient immunity. We wanted to identify it, determine the adequacy of the immunity to those. By the way, those 1039, 1037 is the line number of the document. So in your mind, just ignore those four characters. So just ignore that. When I copied and pasted, I didn't delete the line numbers. Access to the degree of consistency of good EMC design and monitor and control such designs. Well, we would like to monitor and control, but the IPRM itself is a technical report in the sense of it's largely informative. They have authorities that would take that IPRM to implement their SmartGrid design, and therefore it's on that sort of fence of being a requirement vis-a-vis requirement versus a recommendation. Well, it turns out that we've sold that so well that document is more of a requirement than a recommendation. And I won't go into details, but some of you that may be involved in standardization work know that it's easier to get a recommendation published than it is to get a requirements document published. So identify and locate gaps in the design and implement that cause important functions and even cause device failures. You can imagine with millions of smart meters in existence in our country already, what if there's the design flaw that wipes out 10% of them? You can imagine the cost to the utility industry to go replace them. And then what do they replace them with? Do they replace them with a better design from an immunity perspective or not? So the idea again is these bullet items is to raise the awareness of the reader. There is an annex that is part of 7.2 that goes into a little more detail of the types of tests, and I'm going to talk about that in a moment. And you'll find that it's not a surprise to those in the EMC community, EMC test community. So our charter that we put together, I guess it's been a year now, had 10 facets that we wanted to consider for our work, and we then sent out a almost a doodle poll, actually a Survey Monkey, to ask the members of the working group, which by the way I didn't mention is about 25 people from all walks of utility and manufacturing aspects, including some regulators in the power industry. Now, the number of people active as any committee is a much smaller number, but nonetheless, we're getting our work done. So what I'm going to show in the next 3 slides is the 10 items that, and for 2 reasons. One, I'm going to show you what we're doing now and what we have done. And then when you see the others, they are open to starting work. And if there is interest in these other topics, you have access to my email address. If not, it's d.heerman, H-E-I-R-M-A-N, at IEEE.org, IEEE.org. And we will get you on a committee, no problem there. So let's start the list. The first thing we did that was published last year is look at the extent and severity of the immunity issue on the grid. And we published a white paper on that. It's an SGIP white paper, and the white paper is how the SGIP gets their message out. They don't do it by a standardization process, but they do have a catalog of standards that they rely on others, such as the IPRM, which I mentioned is a ANSI NEMA standard. The next one they're working on at the present time, which is directed primarily at test laboratories, is what would be, how would you test and the test setup to measure these smart grid electronic devices, and that's in process. One of the things that you might just think about, and I don't know if I'll get to it later, is if it's wireless control and you want to check the immunity of a device by launching a wireless signal with the launching antenna, with an amp coming out of a power amplifier with a signal source. How do you do that and not contaminate the wireless control for the smart grid, and how might that interfere with the actual signal you're putting on the device to show it's in a radiated sense that it is working or continues to work? And so our test setup document is, as it's progressing, is going to address that in those particular cases. You won't be able to use the wireless control. You may have to use optics and so forth. And again, this is a lot to talk about, and we just don't have time for it here. The third item is review the state of the EMC power grid, current and future. So we have to have some insight as to where we go next, and that would be part of that particular project. Next one is evaluate the impact of high-powered electromagnetic threats, such as HEMP, which stands for high altitude electromagnetic pulse. And by the way, that is a nuclear event, and that is not a zero probability in the terms of the people that work on SmartGrid. Intentional EMI is a concern because terrorists have access to build or purchase a used amplifier in jury rig and antenna, put it in a briefcase, walk up to a utility substation and turn it on and disrupt the control of the grid. And by the way, some of these, those utility substation buildings generally are brick and mortar, if you will. They're not shielded. And you said, well, maybe there's some sense that there's a big fence around to keep people away. Well, in some places in our country, that particular building is about 1 meter away from the fence, and the fence is 1 meter away from the roadway. So park your car and do harm, which we hopefully is, we're trying obviously to put more immunity into devices, and that might be, for example, shielding that near wall with the metal, and not necessarily the whole building, but at least you divert the energy away from going directly into the building. And then there's natural phenomena like geomagnetic storms, solar flares coming down. And the thing about hemp and geomagnetic storms, however, they cover a lot of area. And I'm going to show you a photograph in a moment when we get to the actual report. Continuing on, should there be a conformity assessment program? There is something that would be put into your 17025 scope of work, that you can perform these tests and that would be assessed as a conformity assessment. Provide a guide for performance before and after tests. You can see I put down 2018 because we will never get to that this year because we have a lot of work going on. The other one is complexity of multiple communication protocols. Right now there's about 8 protocols that control the intelligence and the communication channel, and of course you can't build let's say a meter that can handle all 8. So the utility will say, well, we're going to focus on OpenADR or some other distribution communication channel. But the testing organization has to be prepared to get access to these sources. And right now we call it a research project because we haven't gotten that far. Long-term strategy, that's kind of an obvious one. There's another one, multiple cluster of smart meters. There is a problem, a potential problem. If you're in an apartment building with 200 apartments, you'll have 200 meters and they're about, let's say 20 centimeters separated. Well, someone said there's no problem because all these meters will be FCC approved because they meet Class B limits. Well, Class B limits are 3 meters. You have no idea what the device does at 20 centimeters. And therefore, you're really looking at a very low Q, if I can use those words, cluster of an antenna array. And they will interfere with each other, perhaps. But again, this is by the way, this is one of the projects that the National Institute of Science and Technology is interested in working, and I'm helping on that goal with them. Then, of course, continue on this IPRM. So let's look at what we did last year, and I think this will help because I'm going to show some of the material in the actual document. Depending on the time, we'll see how much we can get through it. One of the things you want to look at is the extent of the problem, and these are the questions we asked and tried to answer. Are there credible reports that exist? And you can imagine a lot of these instances of performance degradation may not get reported because you don't want to air your bad linen, so to speak, by saying you have a meter or the utility hasn't done enough. So we have to look for those things that are published in the open literature. Are there hotspots? And right now we find most of them are at the power substations. And what are those problems? Again, I'll talk a little bit later. And can these failures be localized, let's say at the customer location or at the power generation, or is it unfortunately vulnerable throughout the entire grid? And these are things that are, of course, are more important, because obviously if it's across the grid, it's a much greater problem. Then once we have the extent, what's the severity? Fortunately, we have an IEC standard that talks about the field levels. These are radiated now, that are typical of EM environments, and it goes on for 20, 30 pages of tables. And it is at particular distance, separation distances from the source. So even though they might give you typical fields, electric field strength, that might be at, let's say, 10 meters away, but again, if you're 2 meters away, the document doesn't necessarily give you a guidance on how you would insert that information into a near field equation and get a higher number. So we want to gather the data, and we know now that there's real concern with high power pulses, and then of course how you take into account these multiple exposures that I just mentioned. Excuse me. These are the main documents that we are using right now. The classic one is the 61850/3, general requirements for communication networks. That's used on the power utility and is automated. From the IEEE side, we're using 1613.1. That goes into the communication networking, both at the substation and during transmission and distribution. You know, transmission is at high voltage and distribution is a lower voltage. And then when you get to the actual user, it may have a step down transformer that goes to, you know, 120, 220, 240 volts, etc. And that's single phase. Of course, three phase, you just multiply the complexity. The 6-5 was published 2 years ago, and that shows what has been reported, the immunity for equipment used in power station and substation. So with this mix of these 4 standards, we found ourselves in a fairly good position to talk about the general problem with EMII. So just quickly on 6180, I'm just going to go over the general requirement, well, actually the abstract part of it. So it defines general requirement mainly regarding construction, design, and environmental conditions. Now, unfortunately, that is not electromagnetic environmental conditions, which is picked up in another version. And it's at the power substation. And we will talk a little bit more about their test levels in a moment, which does include the immunity issues that I've been referring to. And then when communication cables are an integral part of another device in the power station, then the environmental requirements for the device itself applies to the comm equipment. So they're trying to separate out a network within the building. And of course, the thing that's been used for years is protective relaying, capacitor bank switching in and out for power factor correction and so forth. Continuing on, the EMC requirements now. Now I'm going to get into what they put in. In red, it should be made up front that you just don't use the classical 61000-4-X series for industrial environments, because it's not sufficient at substations because they have higher levels there. So we have to define what those test levels are, and then look at the generic set of immunity standards in the IEC 61000 series, and then also on the protective relaying series, which is 60255. So what I try to do is just picked out a few important cases here. This is in the -3 document. This is clause 6.7.2. Typical applications covered by the technical specification as medium voltage and high voltage. Doesn't say anything about distribution down at low voltage. So this In the document itself, they cite these as examples, and don't forget this document was published back in 2010 and it's been updated, but it still has a reasonable review of what they are most concerned with. Lightning and switching surges, you know, when you break a relay. Strokes and gases, isolated media, which produce fast transients. Traveling waves, well, you can read it yourself, in switchgear, which, in other words, it's more transients that they are most concerned with, or at least they most recognize in this document. And here's the shopping list of standards that are, the one in black is those that were there, and they've been augmented by the ones in red. And, you know, it's the 4-X series, as you can see. And good news is most EMC laboratories do, by the large share of these measurements, if not all, in the black. Maybe they don't get into surge withstand, but it also means that maybe you don't get into DC and AC power point with voltage dips and eruptions and so forth. That's not to say that you may not have special needs that have required that, but looking at this, I consider this good news, because typical EMC laboratories probably do 2/3 to more of these tests. Now the question, of course, is the test setup. How do you get the communication channel to work, and how do you show performance degradation or acceptance criteria, and so forth. So I think this is good news for those in the community that are interested in getting into the SmartGrid testing area. Well, guess what? Those, if an EMC test laboratory, have been doing these tests for decades. Now I'm going to switch over to the IEEE document. You can read the title there. It's, again, works on the communication network in transmission and distribution. So this is now down a little bit lower in voltage in the distribution side. So here's the again, the scope I just pulled out. Establish requirements for communication, networking devices supporting you know, the substation. It addresses such issues as the enclosure, temperature ranges, electrical phenomena, and others that are characterized by a transmission and distribution environment. What you are seeing here is what is generated by its environment, and we are missing the words, which I'll show in a moment, that they have picked up to go into the electromagnetic environment. And in particular, I'm just going to show what is in the 1613.1. And again, there's a gap. The red is those tests were not shown in 1613.1, and now they will be shown. But it's useful to know that at that point in the standard, they're worried about radiated immunity, electrostatic discharge, electric fast transient, and surge withstand. They didn't get into surge or lightning, and that was picked up with the IEC, showing that they want to test to 4-5. And the C standards, C37.90 has been used for testing relay systems for quite some time. This probably decades. And so some of the testing I show up there in parentheses show up in C37.90.1 and .2, and I showed that they were picked up in 1613. Now, a little bit about the test levels. Zone A and Zone B, first of all. Zone A is inside the substation, and Zone B is in distribution, which is outside the substation. Where do you think the line of demarcation is between Zone A and Zone B? If this was a quiz, we would have 5 minutes to solve it. Turns out it's simply the fence of the power substation. And I've already given you an instance where that fence is intimately close to substation building, but clearly in most places there's a lot of acreage. So if you look down, I'm not going to go into every test level, but obviously if it's further away outside the fence, quote unquote, zone B, there are lower test levels. And you can kind of scan them yourself. The ESE numbers are inside are pretty typical of what we would test up to for contact and air discharge. And then we have in the radiated immunity, because the document that was relied upon only went up to 6 gigahertz, and it was actually spot frequencies. So there's an array of some strange numbers from 8.5 to 18 volts per meter. But just keep in mind the 15 and 20 for a moment for the radiated. So the gap immunity test that was not in that list there, you can see the numbers that was picked up there. Conducted, for example, is 10 volts. And the magnetic, 60 hertz magnetic is 100 amps per meter, all the way up to 1,000 amps per meter, and so forth. And these are not uncommon, but and some might say that 30 volt number for the common mode disturbance is pretty much on the high side. But again, you're in a very difficult and severe environment, electromagnetic environment inside the substation grounds. Last thing I wanted to talk before I get to the document and see how far we can get through it is, here's the acceptance criteria. And it runs along the lines that most EMC test laboratories have done. No hardware damage, obviously, is something that is always spelled out in the test plan. No loss or corruption of stored memory or data. Device resets do not occur, and manual resetting is not required. So you don't have a reset, you don't want it to occur, and you don't want to have the ability or need to reset. No stage changes in the states, and now this includes alarms, status, inputs, targets, etc., and nor erroneous permanent change of those particular areas. Momentary changes are permitted, and then of course the supervisory control and data acquisition analog values shall not change by more than 2%. So now you have to have an instrumentation that somehow monitors percent of the SCADA changes. Well, good luck. That's not necessarily easy. And then after the test, the accuracy must revert back to the manufacturer's claimed accuracy. I thought this was this showed up both in the 1613 series as well as the 61850. So here we have international harmonization on at least the acceptance criteria. Sometimes people call it performance degradation, but the more positive of words is acceptance criteria. I just want to make a comment, and I'm going to go back to the document here in a minute. What we're doing right now is working on the test setup document, and our target is the test laboratory as well as equipment manufacturers that have to build these things. We're trying to reference our key immunity test standards, and you can see the list that we're working on, and there will be a white paper. So before I conclude, let me go back to this, and I'm going to bring up, by the way, the second URL down there, if you click on that, it will bring up a webinar that we gave on the 17th of January. It's a live webinar, and it's no fee. All you got to do is enter your name and email address and then click register, and it automatically launches the 1-hour video. But it's very useful in that what I'm going over, it obviously does it in a more compact nature than in 1 hour than a 100-page document would. So that I recommend to you on your own time. I won't propose not to bring it up. Well, maybe I'll just bring it up to show, I'm going back when I said I would do. I put my name in here to start with, and if you register, it's going to actually launch it, and if you had your audio on as well as visual, you're going to see, and again, I don't want to take away from ours, but I'm going to cut it off, but after she gives the introductory remarks from the SGIP, then I take over and chair the webinar and give the part of the document that I wrote. Jerry Ramey from ARC Technical Resources gives the part he wrote, and then Dr. Bill Radowski gives the information on high power transients. And this is high power transient, not high energy. Energy is the power times time. And you can see that what we talk about is a short pulse, and therefore very low energy, but high power. And because of the voltage level, that becomes a problem, as well as the fast rise time. So let me bring up this document and spend the rest of our time on the webinar just kind of scrolling through it. And let's see if I can make it a little bit bigger. And that should be viewable on the screen. And apologize for scrolling too fast, but I want to give a sense of getting to the details. So it's a white paper developed by the SGIP. We published it 2 months ago. And there it is from the EMII working group, my working group. And of course, you always talk about the sponsor and acknowledgments and so forth. And there's the three of us that gave the presentation. And you can see I represent the ACIL on this. And the only one that's not with us right now is Amanda Stallings from the Ohio Public Utilities. She dropped off for the year, and we're hoping she comes back, because it's always useful on these committees to have someone that is concerned with SmartGrid vis-a-vis, obviously, a utility company. So this is a table of contents, and we'll get into a couple of sections, again, the time we have left. We talk about the environment, and then we have challenges, and we show some of the issues that have been recorded. And you can see we had problems with LED light bulbs, switching power supplies, variable C drive, where you can read arc fault circuit interrupters. We had members of the SGIP that had problems with interference in their own home by these interrupters, which is fault circuitry. And then of course there are some interference complaints that the FCC gets, and what's in our document is stuff that's reported largely from the American Radio Relay League, which Jerry is one of their contractors. Then you can see we go right to the extent and failures. I give a little talk on that, and then we go launching into the high power pulsing. So that's kind of what we have, and then of course there's a bunch of tables. So let me scroll and stop occasionally. This report's quite nicely done. You can see there's sidebars there. Devices are defined by equipment that control power and send information bidirectionally. The word bidirectionally is key on SmartGrid. It's not in one direction. So we got into the phenomena, and we pointed out those immunity tests that we consider is important for obviously making the devices more robust against the environment. So you've seen these tables. I just showed you a brief sketch, but we put it in more detail, and we have on the two columns, the second and third columns, where these have been in other documents. And you can see in some cases there are no equivalents on both sides. For example, 61850 has nothing on damped oscillatory magnetic fields, where 4-10 does, and that's covered in IEEE standard 1613. So we're setting the stages that we're not just telling you that there's a problem, but we're telling them, what would be the typical test to show that it is immune to those particular phenomena. And then there's some graphics in here, which is kind of neat. But I want to go into some more text here. So we start with the environment, and obviously it's throughout our communities. And you'll see a figure that you just saw, didn't you? So that sort of sets the stage with the intelligent infrastructure overriding the typical infrastructure that we're used to right now. And that was a chart that NIST put together, which has been used forever. The challenges, and here's some of the challenges we found as problems that would have to be monitored during an immunity test. And of course, some of it is because things are changing in product design. We have faster clocks, we have wider bandwidths, lower power consumption, therefore any interfering signal will have a major impact on signal noise, closer densities and geometries, which has cross-coupling influence with electrostatic discharge, because now you got to realize these meters, for example, in the field, or any electronics, they have to be perhaps maintained, and now we got to train the people in the field, to wear a wrist strap or something so they don't discharge and hurt the electronics from an ESD event. So we have an increasing number, we're setting the stage, increasing number of, we call them softer, numbers more vulnerable to EMC. We talk about a little bit more about it in the challenge. I think I'll move on. Consumer problems. This is the stuff that we have found in the open literature, and I'm just going to sort of scroll through it with the few minutes we have remaining. LED light bulbs remains a problem when it's replacing an incandescent. They have the ability to have more emissions, and as a consequence have caused problems. The FCC has duly noted that. They issued KDBs, knowledge database papers, back in June of last year. Manufacturers and users should therefore note that the lighting are required to cease operation if harmful interference occurs. Well, that's nice, but who do you report to? Who in the field would know the hot number to call the FCC field office bureau to, hey, there's a problem with LEDs? And we show a couple of them because, again, the readership of this document is not necessarily technically inclined. Perceived need for the FCC to issue down indicates two things. There are actual RFI issues with these bulbs, and the need to adjust the scope of radiation emission testing is strong, and there's credible evidence of a real problem, and we do have documented evidence of that. Next area that we've run into issues is, obviously switching power supplies depending on the chop rate, etc., and variable speed drives. The arc fault interrupters was, I didn't realize it was that much of a problem, but it has been, and there's been a lot of reports of interference caused by not operating correctly these interrupters, and we have a section on there of what to, how you might look up. And again, our resource tends to be the ARRL because they publish this material in their documents where you might have trouble finding it someplace else. FCC complaints. Here's a chart of what has been published, and you can see that 66% of the complaints they've received, the red arc, is interference. Now, some of that is repeat, reported more than once. Some of it could be a group of people got together and said, okay, you 15 people report, and essentially make the number more than perhaps it really is. But the point is, it is a major part of the complaint issues that the FCC gets annually. And let me move on. This is an interesting one. at a particular location in, this was Illinois, I think, there was a customer that had a sign that said open, and in the window, in the storefront window. And it turns out that when the vehicle is parked along the curb with the store over here, and they had automatic door locks, it would, if they got parked, the car would lock itself and it would not be able to be unlocked due to the interference, and the key fobs just didn't work. So it was reported, and someone came out and looked at it, but they didn't have a real thing to tell them to turn this open sign off. So the fix was, maybe you get a chuckle out of this, was just don't park in front of the building. Well, if you don't park in front of the building, isn't that a deterrence to go into the store to pick up goods or donuts, whatever it is? And it was a switch mode power supply on that sign, that neon sign. It's still going, and people are still not parking. By the way, these cars had to be towed away. A lot of vehicles have had problems, and by the way, this is the set that we could find in the open literature. It's a lot of different manufacturers there, right? And we got about 3 minutes to go. We also showed some of the other things. That this one showed up in WABC News. A digital camera was brought too close to a control panel at a nuclear power plant in Long Island, and it caused the water level alarm to shut off, and the water level started to drop. And this is just with a camera close by, not even flashing. So again, we picked up as much as we could find in the open literature. So I've already talked about these questions in earlier, so I'm going to bypass the questions, severity and extent, because we've already looked at them, and just very briefly show that we have a whole section on severe environments, which is the high-powered transients. And there's a graph here I can show before we go off the air. Getting to it. This is the high altitude impulse, and just look at the axes. And E1 is early time, E2 is intermediate time, and the times are if you look at the seconds, for example, get to 1 second, you're already out 2/3 of the way on that pulse, and you can see that the level in volts per meter is over 10 to the 4th. So you're well over, you're into the 10,000 and plus with a very prompt, fast rise time. And also, in addition, in these kind of events, you have gamma rays and other things going out. So this should be a concern. Why? Because an event such as this is not just one isolated power substation. It affects a large area of the country, as do geomagnetic storms. So maybe the last one I'll show is, well, this one here is sort of the spectral density, but the wideband communication channel is right here at the purple one, if you can read it. Starts at about 300 megahertz. So these are the controls that's been put onto the grid in the frequency range. And then I think I'll go to the geomagnetic storm, which is a kind of a classy photograph. Boom. Here, left is the sun. The rays, the ionosphere is disrupted, and the effect goes right through a large sense in the direction of the Earth, and close that down. And this is the event that is in, that again is published, happened back in '89. But the red is the high intensity of the geomagnetic storm disturbing the ionosphere and therefore coupling into the power lines, because what is a long power line? It's an antenna. And the red dots on the right are the power substations that went down in 1989. And it wasn't just in the Northeast, it wasn't just in the central part of the country, it even went into Canada and California. That's why geomagnetic storms are really of interest to those in Congress even that are worried about electromagnetic interference and effects. So I think at this point, I'm going to conclude with the conclusion. The EMII work investigated the environment where smart grid devices are used. Instances of disruption in the smart operation has been publicly identified or included. The working group found that the environment varies considerably, and the report concludes that we'll need more immunity assessment to these signals to the devices. And the good news that these tests have been identified in the report is gratifying that such tests in general are widely deployed by AMC testing laboratories and hence are readily available for smart grid immunity assessment. So that is the setting the plate, and now it's up to the laboratories to get involved and get to know more. But again, we now have for an EMC laboratory side of the house, we have a complete open tunnel to get into this work. If there's a business need that makes sense to do so. So with that, I'm going to conclude the webinar. Again, thank you for participating. And if you're looking at this on delayed recording, my contact information is d.heirman, H-E-I-R-M-A-N, at IEEE.org. And with that, I thank you for your attendance, and we stay tuned for the next webinar, which will be in May.